Okay, so let's start with the last lecture of the course. So in the last lecture, what we saw is how to interpolate images. So now what we will do is how to use those interpolation schemes to do some other operations with the images. And the operation we will see is these geometrical transformations, which are called here warping and rotation. So warping is geometrical transformation. Rotation is a particular case of these geometrical transformations. So the idea is you have an input image, and then you have some warping function. The warping function is a function that tells you each coordinate in the input where it should go in the output. So you have the warping function, and then we can go both ways, actually. So we can go, let's say that you have an input image here. So you have your input. Typically, we have said I for the input, and then we have J for the output. And this is Rj, this is Ri. And then you need a function that is the warping function, let's call it F, that transforms coordinates from I and gives you Rj. And then you have the opposite. So you have the inverse of that function. So given J can recover the coordinate in I. So typically it is applied in this way. So from the output to the input. So once you know the coordinate in the input, now you can interpolate the input image at that location. That is what is represented here. So you go from the output to the input, and then you interpolate the value there, and that is the value that you put. So for instance, this house that is somehow tilted, you can put it straight. So yeah, this is what I just said. So it is if you want a geometric remapping. So let's give an example. So let's say that you have this castle, and then we wanted to, so there is some kind of perspective distortion. So these towers are not straight. So let's correct for the perspective. So that is what we want to have at the end. So what we will do is you will have to give pairs of coordinates that you want to map through this mapping. So you have to give me pairs of Ri and Rj coordinates. So let's say that these are the coordinates in Ri, so in the image I, and these are the coordinates in J. So we are still displaying image I, but you see that the coordinates, we have put these, this coordinate has stayed the same, but this one, we have put it straight. So let's look at the values again. So the bottom coordinate stays the same, but this one, we will shift X. So we will shift X. So Y will stay, but X is shifted to be straight with this one. Okay, and the same for all the others. Okay, so we make the two X coordinates to be the same in the bottom and the top of the tower. Okay, so this is what we would like to have. So let's see if we can achieve that. So to do that, you will give me pairs of coordinates. So you will give me, here these are represented as X, Y for the input coordinates, UV for the output coordinates. So let's put it like this here. So let's make the same reasoning, but now with our notation. So what we are saying is you have a coordinate I. Let me see in which direction we are going. So we are going H goes from, okay, H goes, yeah. So we have this coordinate. Space. Then we multiply by H and we will have Rj1. And this will be a matrix. And this will be another matrix. So the first coordinate in I has to be transformed into the first coordinate in J. The second coordinate in I has to be transformed into the second coordinate in J. And so on for all the coordinates that we have. So we have a matrix here. So this matrix is of which size? So we have 2 columns and p rows. So it is 2 times p. This is 2 times 3. And this is 2 times 2. So we can, sorry. So now we can solve for h. And for h, let's call this matrix the matrix Rj. Let's call this matrix the matrix Ri. And now you know how to solve for that. So you multiply. So what we have is this equation, Rj is equal to H Ri. So you multiply on the right by Ri transpose. So you have Rj Ri transpose is equal to H Ri transpose. And now this matrix is of size 2 times 2. That is also size 2 times 2. And then simply you invert by that matrix. So what we have is Rj Ri transpose. Then Ri transpose minus 1 is equal to H. So now we have our H. And this is the matrix that we should use to transform the coordinates from I to j. And if you want to go in the other direction, you simply multiply by h minus 1. Okay. Yeah. Okay, so this is what they are doing here. So h minus 1 that multiplies coordinates in the j space. And then that will give you the coordinate in the I image, and then you interpolate the I image at that location. Very good. So yeah, it is the same equation I wrote. I prefer my notation. I think it's more clear. But here it says how not to do it. So let's see why. So let's say that we have our coordinates. These are our pairs of coordinates. We do the calculation. This is h minus 1. And that is something interesting. That is, this h or this h minus 1 is only affecting x. You see, y remains unchanged. So when you multiply, we have a matrix of this form. So we have a matrix of this form. So A, B, 0, 1. And then if you multiply Ri, that is, so if you multiply, this is h minus 1. So when you multiply by h minus 1 times xj, yj, this will be a xj as b yj, and yj stays the same. So we are just touching x. That is what we wanted. So we want it here. So our coordinate transformation, y stayed the same and x was changing. So that is what this matrix has achieved. Very good. So then this is what we have. This is the blue one. So red lines is what we have. The blue ones is what we want. We still have the original image. And when you apply it, okay, the transformed image, it is a little bit closer to the blue, but not quite. So it is not just on the blue. So it is a little bit better than before, but not so much better. So why is that? Yeah, and by the way, before we get into something else, is that any matrix can be decomposed in this way. This is called the singular value decomposition. So a singular value decomposition, you are familiar with the eigenvector decomposition, right? No? Eigenvector decomposition? No? Diagonalization of the matrix? Yeah.
En Spanish.
¿De qué? Autovalores, autovalores, autovectores.
Sí.
Okay, so what that says is that the eigen value decomposition says any matrix can be decomposed as PVP minus 1, and this is a diagonal matrix. But there is a constraint on this, that is that this matrix has to be squared, and then all these matrices are squared. So what happens if I have a non-square matrix? If I have a non-square matrix, the eigenvalue decomposition doesn't exist. So what exists is the singular value decomposition. So the singular value decomposition, it is kind of similar. So you have so these two matrices now are decoupled. So in the eigenvalue, it is the same matrix that is inverted, but now in the singular value, they are decoupled. So this matrix and this matrix are different. And then we have a diagonal matrix in between. So this is our diagonal matrix. And these two matrices, they are orthogonal. So orthogonal means having determinant 1. Having determinant 1 in images means that you are applying a rotation. Okay? So what it means is that you are making some rotation, then you are doing some scaling, and then you are rotating back. So let's see, this is the singular value decomposition of our previous transformation. So we have some rotation matrix, and then some other rotation matrix, and then our scaling. So that means that any transformation can be understood as first the rotation. So first we are applying this one. So we are applying that rotation by 90 degrees, 19 degrees. Then you are doing this scaling, but this scaling, this is enlarging the x-axis and shortening the y-axis. So first you rotate, then you scale, and then you rotate back. And any transformation can be understood in that way. So always first the rotation, then scaling, then another rotation. Okay, but then we haven't fully succeeded in putting our towers straight. So let's see why. The problem is that the transformation we have devised, this transformation here, this age, is a pure 2D transformation. But the problem was created in 3 dimensions. So this is a 3-dimensional object, and because of the perspective, we have this tilt of tilting of the towers. But so it was a 3-dimensional problem, and somehow we have given it only a 2-dimensional solution. So let's see if we can give a 3-dimensional solution, or some solution that is better. And the trick to do that is constructing these homogeneous coordinates. So to use coordinates that really have, or to give more freedom to the matrix H. So to do that, what we will do is to construct homogeneous coordinates. So these homogeneous coordinates is the following. So let's So let us represent the homogeneous coordinates with a tilde. So now this will be our coordinate. And let's say this, I don't specify if it is x, I or j. So we had an original coordinate that was x, y. And now the homogeneous coordinate corresponding to that is kx, ky, k. So that is a mapping between, so if you want, if you are going from here to there, you have to multiply by k. If you are going from here to there, you have to divide by k. So if you have an homogeneous coordinate, what you have to do, so let's say that I have the homogeneous coordinate, and I have this homogeneous coordinate, it's called x, y, z. So, and I want to know what is the coordinate that is the standard one, so the normal to the coordinate. So this would be r would be x divided by z, y divided by z. And so that is given one to the coordinate. The homogeneous coordinate is there are infinite homogeneous coordinates that can represent the same point. Okay, so we will, in one of the spaces, in the input space, we will use this homogeneous coordinate with 1. In the output space, we will use this homogeneous coordinate with k. And this k we will have to solve. Okay, so this one is fixed, but this one will be free. Okay, so what next? So now I have pairs of homogeneous coordinates. So now I have this matrix of input coordinates in the input, this matrix of coordinates in the output. These k's are something that I have to figure out. Okay, so they are unknowns. And then my matrix now will be 3 times 3. So I have much more, many more degrees of freedom to tune my numbers here such that these correspondences are better fulfilled. Okay, so now let's look for the age. So to look for the age, what we will do is set up or analyze further this coordinate system, this equation system. So this equation system says when you multiply this matrix times this coordinate, it has to be equal to that one. So that gives us 3 equations, and this is just the same equations as we wrote before. Before it was in matrix form, now they are the equation system. And now what we will do is divide the first equation and the second equation divided by the third one. So if you divide, now the ki disappears, and what happens is this thing. So ui and vi, that are the coordinates in the output, will be those 2 ratios. And these this matrix H, because of this ambiguity that there are for any given point, or here, for any given 2D point, there are infinitely many homogeneous coordinates. That means that you have to fix something if you want to solve that equation system. So we will force H33 to be 1. Okay, so we will make H33 to be 1. So we divide numerator and denominator by H33. And we are abusing the notation. This would be H11 prime, but we are removing the primes. So this H11 is not the same as this one. Okay, but so far we didn't didn't give values for those ones. Those were our unknowns. So this is our new equation system. Okay, very good. Now we simply put the denominator to the other side. We have this thing, and you bring everything to this side. You expand these parentheses. So now you have this equation. Okay, so let's look at the equation. So the equation, our unknowns are the h, and our data is x, y, and u and v. So what we have is this equation times h, this row times h, this row times h. So this h is this vector, so it is h11, h12, and so on. UI here, it is coming from this product, so 1 times UI. So there is this one. This one is the full row multiplied by h. Yeah, the last element of h is 1. Yeah. Okay, and that is for a single point. But now we have many points. So if you have many points, now you have all those points. Okay, so now what we have is to solve for h in this equation system. A times h is equal to 0, because the right-hand side in all these equations is 0. So a times h has to be 0. And one possible way of solving that is this one that is here. Is you do the singular value decomposition of A, that is this expansion. And this expansion will have some, so it has a diagonal matrix with the singular values, and it has somehow the equivalent of the eigenvectors, but now they are the basis of a column space. So here we have the basis of that column space. Okay, one of these singular values will be the minimum one. One of them is the minimum. So let's say it is sigma 1. So if it is sigma 1, we have to, our solution is V1. So if in general, if the minimum singular value is the number k, so the corresponding column in this matrix is the h we were looking for. Okay, so now we have the h there. So you put it there, that is our vector vk, and now you have h. So that h is the one that helps you to go from one image to the other. Yeah, and this is what I explained, that if you have a coordinate that is an homogeneous coordinate that has 3 components, the second and you want to find what is the coordinate in the input image, what you have to do is to divide by the third component. So that equation is the equivalent of this one. Okay? So if you have 3 components, you have to divide by the third one to get the 2D coordinate you are referring to. So these ones, just a reminder, they're called homogeneous coordinates. Very good. Okay, so this is just an explanation of the same thing we have been discussing. And it doesn't show, but the result would be closer to the one that we want. So we want this one. This is the one we have obtained with these homogeneous coordinates. Okay, good. So any question up to here? Okay, so the last thing is, or the last part of the lecture is about rotations. Yeah.
And what's the difference between AJ plus two H RE and the other method, like the
What are the,
three,
so where are you?
like,
Here?
yeah,
Okay,
like the first in the beginning,
this one,
no, like before.
the very beginning. This one here?
Yeah, the H R and the other that
Yeah. What is RI and RJ?
like the difference between RJ equals HRI and the other like A equals like the three.
Can you spell it? RI equal?
RJ equals to,
This one.
yeah, and the other like
A,
equals,
capital A.
yeah, so equals to B.
Okay. Now this is a general. So this is the eigen decomposition of a matrix in general. So any matrix, for any matrix, this is the eigen decomposition. And if you have matrix H, you would have, if you have the matrix H, you would have a P for that H, diagonal for that H, and a P for the H. Okay. If this is a square, if it is a rectangular matrix, then you cannot do that.
So the amplitude is the wrong one, like the resolution.
Yeah, it is not that this one is not actually I mentioned this only as a way to say you know the eigenvalue decomposition. You don't know the singular value decomposition, but you know the eigenvalue decomposition. So the singular value decomposition, this one that we have been using, is somehow equivalent to the eigenvalue decomposition that we know. But we will use the singular value, not the eigenvalue.
Yeah.
Okay, and then why the previous one was wrong is it is not wrong. It is that it is not as powerful as this one. So because before you had only 4 values to touch. So you have only 4 degrees of freedom to make the coordinates match. While now you have 9 degrees of freedom. So now you have 9 degrees of freedom. So now you have more freedom to make the coordinates match. And actually, somehow this represents better the geometry that your coordinates were coming from 3D coordinates that were projected onto a 2D plane. Okay. Very good. Any other question? Okay, so then let's go with rotations. So let's say that you have an input image and you want to rotate by some angle, theta A, and actually he's very picky about theta A is the angle between the diagonal and the horizontal axis. He's very picky about all these details about the corners, not corners, or everything. So I will concentrate rather in this part of the rotation. So important thing there is the following. So rotation matrix. So we have actually we can reuse this drawing. So let's say that what you want is to rotate this image. So in one direction, let's say that our transformator is Rj is equal to H Ri. So the kind of H matrices that perform rotations are these kind of matrices. Remember one inside. So it doesn't matter, but just to be consistent with the slides. So these kind of matrices, they apply rotations, and they have a property that is that the determinant of H is 1. And so to go in one direction, you multiply by this. To go in the opposite direction, you multiply by the inverse of that. And the inverse, I will draw it here in blue. The inverse is exactly the same, only that this is a plus and this is a minus. Okay, so it is just rotating in the other direction. Okay, so we have this equation. This equation allows us to go from this coordinate to this one. But this is assuming that we are rotating around the center of the image. So, and if it is not rotating around the center of the image, we already know the trick. So what we have to do is to center the coordinates. So let's say that our coordinates are not centered. So what I will do is I will take the 0 coordinate in the J space. And this will be C. Okay, so what I do is, so these coordinates are not centered now. Okay, so these coordinates, so it is more convenient. Okay. So it's more convenient to make this axis pointing down. Let me do it pointing down like this. So, and we have some other coordinate system that is based there. So in this equation here, this is in the coordinate system that is not centered. This is also. But this thing now, there are coordinates in the coordinate system that is centered. And the origin is here. Okay? So the origin this is R0, RJ0, RJ0, and this is not so, RJ0, and this is RI. Okay, so you have two coordinate systems, one that is centered in the middle of the image, another one that is not centered. So if you want, this is the center coordinate. So this equation is true for the center coordinates. And if you need to center, first you subtract this one. And sometimes you prefer to write in this way. RJ is equal to RJ no, plus H RI minus RI. And this is the equation that is in the slide. So in the slide, you recognize this kind of pattern. So it is the coordinate center in the output image, and then the input coordinate that has been subtracted the mean or the origin of rotation. And this is the rotation matrix. Okay, and then there are many slides discussing what happens if my image, when I rotate, let's say I start with the blue image. When I rotate, there will be some corners that are outside my output image or my input image, and then I have problems in the corners and all that. So it is true. When in the borders, in the image borders, you always have problems when you rotate, when you perform convolutions, when you do the Fourier transform. So the image borders, they always behave differently. Okay? But we will not care in this course about the borders. Okay, so there is a lot of discussion here, how wide my image should be and so on. We don't care about that. So if you rotate and you want to still keep the full image, you have to make the output image to be bigger than the input image because of the rotations. But yeah, we don't care. In this course, we don't care about this. Okay, so all this is related to that. So what we care is about this thing. So how to perform transformations between coordinates. And in general, this coordinate will be, this one is integer, but so Rj is integer, but we normally go in the other direction. So we normally go, instead of from input to output, we go from output to input. So you would have to solve for Ri there. And then Ri, when you go in the opposite direction, in general, it will be a fractional coordinate. So a fractional coordinate will be somewhere in the middle there. But now we know how to interpolate, because the previous lecture was about image interpolation. And here you have some examples. So we take that image, we rotate, and we rotate using two methods. So we know that the cubic is the most accurate interpolation. So we compare nearest neighbor to the cubic, nearest neighbor to bilinear, and then we see that okay, there are differences. So the way you interpolate causes differences, and most of the differences are where the boundaries of the image are. So this area that is very flat, you almost have no difference because it doesn't matter. This is almost a constant. So nearest neighbor, the cubic and bilinear, they will all estimate a constant there. And this nearest neighbor to bilinear, bilinear to be cubic, so all kind of interpolation comparison. Okay, all the comparisons. Now, what is very interesting is that we have explained very simple geometrical transformations, but we can perform more fancy transformations. So let's say that we have a sphere that is reflective, so it is a mirroring sphere. So, and we want to simulate how a particular image would be seen in that sphere. Yeah.
Is this, for example, the Mercat or Mercator one placing its own?
Yeah, for instance, you can also do that. Yeah, all those are just geometrical transformation of coordinates. Yeah.
Okay.
So the way to do that would be the following. So first you have to define a few parameters. So you define, you have the R out, C out, this is the number of rows, number of columns in the output image. And then you define row this way. You do the kind of similar thing for the input image. And then for each output pixel, so this is the coordinate in the output, you compute the polar coordinate. So you compute its polar coordinate. So the polar coordinate is, this is the radius, this is the angle. And now we will define another angle. This angle is rho, that is this one, divided by rho 0, and then arc sine of that. And that will give you rho, theta, and phi. And now we will compute this d. This d is using d0 that is coming from here, and phi that is coming from here. And now we have to interpolate in the input image at this location, d sine of theta, d cosine of theta. So this is the input coordinate from which we have to interpolate when we want to fill this coordinate here. So we take a coordinating the output, and we need a way to go. This is the same we did before. So we, given a coordinate in the output, we need a way to go to a coordinate in the input. But this way, the ones we have explained so far, they were very simple ones. They are just linear transformations. But this example here is a non-linear transformation. But it gives you a lot of power. If you know how to make these transformations, then you can simulate how that image would be seen in this sphere. That is reasoning about that equation. So the important thing is that as long as you know how to transfer coordinates, then you can change your mapping, and then you can change the shape of your image. Any question?
It will be like very fast. How to do the transform in this?
Yeah, in this particular example, you take a coordinate in the output, that here it is represented R out, C out. Then you compute this polar coordinate, so it is the radius, and then the angle of that coordinate. And you compute phi. Phi is defined as the arc sine of this rho divided by rho zero, that is this thing. And now you have phi, and you have theta. Okay, so you have phi, you modify phi and transform it into d using d0. And then once you have d, this d and theta give you the polar coordinate in the input image, and then you simply transform to the Cartesian coordinate. Yeah, so through this complex path. But you always have to do the same. So you always have to go from the output to the input. And ideally, so you should know how to go both ways. But it is enough to go from the output to the input. Sorry?
Like from the result to the
Yeah. Yeah. Any other question? Okay, so then otherwise we'll stop here.